Hello students, in today's class I'm going to start a new chapter, that is chapter 12, alternating current. In this chapter we are going to discuss about how current is generated and what will be the equation of current and voltage so generated when magnetic flux changes. Okay, till now we are studying about magnetic flux. Now we will discuss about the current, that is alternating current, which changes, or it is like a sinusoidal wave. The first topic which we are going to discuss is induced voltage developed between the ends of a coil revolving about an axis in a magnetic field. Now, this topic is what you have studied in class 10 while studying AC generator. When you generate current from a generator, then the same type of diagram is what you have studied. You have taken a coil. Okay, in this diagram you can see you have taken a coil, and when you rotate this coil in the magnetic field region, what happens? Induced current will be generated. So over here it is the EMF which will be generated when this coil rotates. Okay, that induced EMF is the induced voltage which gets developed between the end of a coil. Okay, between these two ends of a coil, induced voltage will be developed, which gives rise to the alternating current. So that is what we are going to discuss. Now, when a closed coil is rotated rapidly in a strong magnetic field, the number of magnetic flux line passing through the coil changes continuously. Okay, this is magnetic. Suppose imagine there is a region of magnetic field. Over here there is magnetic field region passing from one point to another point, and you take a coil, this kind of a coil, and you rotate rapidly. Okay, right now if magnetic field line is passing from this side to this side, then this coil is not being in touch with the magnetic flux. So zero magnetic field lines are passing from this coil right now. But when you rotate this rapidly, right now the flux line will change. Now there will be many number of flux line passing. Again, when you rotate this, it will be zero, again maximum, again zero. So the number of flux lines keeps on changing when you rotate a coil. And when the number of magnetic flux line changes, it gives rise to induced voltage, which in turn gives rise to induced current. Now, the direction of this current is given by the Fleming's right hand rule. In fact, the mechanical energy expanded in rotating the coil appears as electrical energy in the coil. Now in this figure is shown a coil of a wire placed in an external magnetic field B. It can be rotated clockwise about a horizontal axis perpendicular to the field. Suppose initially the plane of the coil is perpendicular to the magnetic flux line. In this position, the number of flux line passing through the coil is maximum. So it is this position. This is magnetic flux line. It is perpendicular. So maximum number of flux line will pass from this particular coil. When it is parallel, it is minimum number of flux line which passes through this coil. So the change in magnetic flux line gives rise to current or induced voltage. So first of all, let me write the equation of magnetic flux. Flux is B cos theta multiplied by area. B is strength of magnetic field. Theta is the angle of rotation, about what angle it is rotating. A is the area of this particular coil, or this equation can be written as BA cos theta. Now this theta depends upon how speed or how fast we are rotating this coil. So the theta, it actually depends upon the velocity of the coil, which is changing with time. So theta is equals to velocity multiplied by time. This is angular velocity. Okay, not your linear velocity, but angular velocity multiplied by time. So let us replace this over here. Now we get flux is equals to BA cos omega t. So when we rotate this coil, what changes is theta keeps on changing. With that, what changes is the number of flux. Sometimes it is maximum, sometimes it is minimum. So rate of change of flux over time will be there. Okay, this is rate of change of flux with time. So what you have to do now is you have to differentiate this particular equation with respect to time. So differentiate BA cos omega t with respect to time. So when we differentiate this, I'll continue this over here. When we differentiate this, B is a constant, that is magnetic field. A is the area of the coil, which will be constant. Now we need to differentiate cos omega t and also omega t separately. Okay, we need to differentiate cos omega t and omega t separately. So BA remains fixed. I'm continuing this over here. BA is fixed. Differentiation of cos omega t is minus sine omega t. Differentiation of omega t will be omega. So rearranging this, it will be minus BA omega sine omega t. This is what we get. That is the rate of change of magnetic flux over time. Now, by Faraday's law of electromagnetic induction, the EMF induced in each turn of the coil is minus n d phi by dt. This is from the Faraday's law of electromagnetic induction, or what known as Newman's law. So over here in this case, our induced voltage is represented by V. Okay, EMF is represented by V, that is induced voltage. Now in place of d phi by dt, we are writing this given value, minus BA omega sine omega t. So now rearranging this, minus into minus plus, it will be nBA omega sine omega t. This is our induced voltage in the coil when the coil is rotated with this velocity, that is angular velocity omega, in the given time t. Now this shows that the magnitude of the EMF induced in the coil rotating in the magnetic field changes continuously with time. The maximum value of sine omega t is 1, and so the maximum value of V is NAB omega. So maximum value of this induced voltage will be when sine omega t, when the value of sine becomes 1. Okay, because you know that the value of sine, it varies from -1 to +1. So maximum is +1. So the maximum value of this will be nBA omega when sine omega t becomes 1. So this will be represented by V naught. V naught is the maximum induced voltage developed when the end of a coil rotates, it's revolving about an axis in magnetic field. So this is V naught. Now let us substitute this value of nBA omega in this equation. So your V, this is V, is equals to V naught sine omega t. Okay, this is the induced voltage in a coil, V naught sine omega t. Now let us see what happens to the voltage when we rotate it in this plane. So this has a different position of the coil in uniform magnetic field. Now initially the plane of the coil is perpendicular to the field B. We start with this position. Initially it is this. So initially in this position your theta is 0. So initially in this position angle is 0. So if angle is 0 over here, your V becomes, okay, in the first case V is equals to V naught sine omega t. Sine 0 is 0 Okay, sine 0, the value of sine, when this part theta becomes 0, it is 0. So V becomes 0. Okay, V is 0. So in this position, the position of the voltage is 0 degree. Let us keep this point as 0 and let us keep somewhere as maximum. Now the second condition, when V, it is rotated 90 degree. Okay, it is rotated by an angle 90 degree. Initially it was this. We consider this position as 0 degree. Now it is rotated 90 degree at this position. So when this angle becomes sine 90 degree, sine 90 degree is 1. Sine 90 is 1. So 1 into V0 will be V0. This V0 is maximum. This is maximum. 0 is minimum. So let us keep this point over here as maximum. This is an axis, that is omega t. Theta is changing continuously with time. So we'll plot a graph over here. In the third condition, again it rotates 90 degree. So 90 plus 90, it is 180. So now V is equals to V0 sine 180 degree. Sine 180 means 0. Again it will be 0, which is minimum. So in this position, it again comes back to, in this 180 angle, it again comes back to 0. And this 90, it goes to maximum. Now in this one, after 180, again when we rotate 90 degree, we get V0 sine 270 degree, which is minus 1. So this becomes minus V0. Okay, minus V0 means it is maximum but in the other side. So this over here is maximum over here in the other side. Okay, this is 270 degree. Now ultimately we come back to the initial position after rotating 360 degree. After rotating 360 degree, we come back to the initial position. So sine 360 degree is again 0, which is minimum. So again we come back to 0 position after rotating 360 degree. So now let us join this from 0 to 90, 90 to 180, 180 to 270, 270 to 360. So we get a sinusoidal wave, this kind of a wave. So this is the wave for the induced voltage when we rotate in a uniform magnetic field. Now thus in the first half rotation of the coil, the voltage induced in the coil rises from 0 to maximum. So in the first half, when we rotate the coil from 0 to 180 degree, it rises from 0 to maximum, again back to 0. And while in the next half rotation, the induced voltage rises from 0 to maximum in the opposite direction, then again becomes 0. This process is repeated again and again. Okay, when we rotate this coil, this wave is repeated again and again. The current which flows through the circuit due to this alternating voltage also changes continuously from 0 to maximum, 0, again maximum in the other side, then again 0. So this type of alternating current, okay, in one and other half rotation is known as alternating current, which changes according to the voltage. This kind of current will be known as alternating current. So the equation is similar to that of the voltage. Now for alternating current, the equation is I is equals to I naught sine omega t. Why the equation is same? Because the current also changes in the similar way as the voltage changes, because voltage is directly proportional to current. Now this voltage, induced voltage, is giving rise to induced current. So voltage is the main reason from where the current is being generated. So equation will be the same. When voltage becomes 0, current also becomes 0. When voltage becomes maximum, current will also become maximum. So this will be the equation of current. Now I'll show you the graph of current and voltage in a same graph. Okay, this is the graph of current and voltage. This axis over here, y-axis is voltage and current axis. x-axis is the time axis. Okay, this axis is the time axis. Red line denotes voltage. This is the voltage. Blue denotes current. Wherever the current is 0, voltage is also 0. Equation of voltage is V is equals to V naught sine omega t. Current is I naught sine omega t. So wherever the current is 0, voltage is also 0. Voltage is maximum. Current is also maximum at the same point. But remember that the maximum value of voltage is always greater than the maximum value of current, because there will be some sort of current lapse when we do this kind of thing. We'll study that later on. But maximum peak value of current, this is the peak value where the voltage has gone to its maximum value, is the peak value. Okay, this is known as peak value, which is denoted by V naught. Now the current over here, this is the maximum of current. This is the peak value of current denoted by I naught. So peak value of current V naught is equals to NBA omega. We know that. And peak value of current is also NBA omega. Is still the same. Peak value and voltage of and this current is same. So this is an alternating graph of alternating current and alternating voltage. So now there are few terms which we need to understand. First of all, let us see in the time axis. This is when time is 0. Okay, this is half rotation. That means not a complete time period but half a time period. Okay, before starting time period, let us first discuss about few terms, some definitions regarding alternating current and voltage. First one is maximum value or peak value. I told you this is the maximum value of the voltage. This is the maximum value of current, which is known as peak value, which is also known as the amplitude. The maximum displacement from this original line is known as the amplitude. So V naught and I naught represents, okay, this line over here is V naught, this is I naught. V naught and I naught represents peak value or amplitude. Now periodic time. If one complete rotation of a coil rotating in a magnetic field, the current produced in the circuit rises from 0 to maximum value in one direction, falls from maximum to 0, again rises from 0 to maximum in opposite direction, then falls to 0. This is called the cycle of the current. So in one cycle, it rises from 0 to maximum, goes back to 0, 0 to maximum in the other side, again goes back to 0. So here it completes one cycle. So again it starts from 0 to maximum, maximum to 0, again 0 to minimum, maximum in the negative side, then again you're back to 0. So in this whole graph, current and voltage has completed 2 cycles. Okay, it has completed 2 cycles. So the time taken by alternating current to complete one cycle, okay, to complete one cycle from this point to this point is known as periodic time of the current or voltage. So if this is T, this point is T, it has completed one cycle over here T. So this will be T by 2. Okay, then if this is T, then it has started another cycle from here and completed it over here. So this will be 2T. So this is 2T, and this point over here is half of 2T, that is 3T by 2. Now the value of time period. How will you find the time period? Time period is equals to 2 pi by omega. This is the formula for time period. Now another one is frequency. The number of cycles completed by an alternating current in 1 second is called the frequency of the current. So if this from here to here is 1 cycle, so in 1 second a current and voltage will complete many such cycles. So that cycle is known as frequency. So frequency, the formula of frequency is F is equals to 1 by time period is equals to 1 by 2 pi by omega, 2 pi divided by omega, which is equals to omega by 2 pi. Whatever is the time period, frequency is just the opposite. Now, the unit of frequency is cycle per second or hertz. Anything you can write. The frequency of domestic alternating current, the current which comes in our household, the frequency of that is 50 hertz. It means that in 1 second, the current which we receive in our house produce this type of a cycle 50 times. Okay, it produces 50 times. So 50 times it is at highest value, and again 50 times it is at the lowest value. It also means that alternating current in electric bulb, wires or bulb flows 50 times in one direction and 50 times in opposite direction in 1 second. Since in one cycle the current becomes zero twice. Okay, in one cycle, whenever it points over here, it becomes zero twice. Hence the bulb lights up 100 times off and 100 times on in 1 second itself. That is, in 50 cycle, it is 100 times switched on, 100 times switched off. But due to persistence of vision, it appears lighted continuously. Because in 1 second, you cannot imagine 100 times a light of bulb getting switched on and off. So what we see is, we see light continuous, but it is not continuous. It is getting switched on and off 100 times in 1 second. Okay, so these are the basic terms of in this chapter, that is alternating current. So with this, we'll stop our class over here itself. We'll continue in the next class. Thank you.